Hello everyone, good evening. Today I'm going to talk about image to sentence generation project. As the name implies, the project it's the process of generating the textual description for an image. And the another synonym for the image to sentence generation is the image captioning as well. And the dataset being chosen is the Flickr dataset, and the technology being used is the CNN and LSTM are two deep learning models. And the benefits of this use case is having more enhanced security for the surveillance camera images and improving the assistance for the impaired individuals, and then more categorizing and organizing your large image dataset by having a search feature. And the drawbacks of the challenges being seen working on this project is like having a limited data, because of the limited data, having a low blue scores for the generated captions. So it could have been improved by having a larger data set and also having an attention feature by using a transformer architectures. And in terms of results, as I mentioned, the blue scores are comparatively lesser values, like around zero point 0.3. And this is the problem statement, like we have to as we know, like the images are getting generated like at a rapid pace, and there poses a challenge of how will you identify those images and segregate or group those images, right? So the basically the image captioning or image to sentence generation aims to provide a solution to that particular problem. And the solution which I implemented for the image captioning is combining the two deep learning models. So as we know here, like if the one is the CNN for extracting the feature, and another is the LSTM for the sequential data generation process. Yeah, and the architecture basically consists of three components: the CNN model for the feature extraction, the sequence processor using the LSTM for the sentence, and then the decoder. So the image feature vector and the image caption embedding are fed into the decoder layer with a softmax function to produce the probability for all the possible words in our vocabulary. And this is the dataset, the Flickr dataset, and it contains an image. And for each image, there are five captions. So in total, like 40K captions. So as we go here, so yeah, like as I mentioned, the dataset is being stored in the drive. So it looks, if you look at the Google Drive, so this is the folder on which I have stored all my dataset. So this is the textual data and this is the image data. When we go to the images folder, you could see the sample image. And when you go to the textual data, so if you look at this token, so for each image, as I mentioned, there are five captions. So they are been indexed with 0, 1, 2, 3, 4. And for the same image, we got the five captions. A child in the pink dress is climbing up like a girl going into the wooden building. So this is how the input dataset looks like. Right. So once the data is in the drive, so we use these functions to mount that drive. That way we can read the content into our notebook. So as we know that the first thing is like doing some data analysis on our data set, right? So what we do here is, this is for the text data set, the path, the directory path, and this is for the images. Contains the captions for each image, as we just saw that it contains an image name and then the index and then the caption. So we create a data frame out of it, like with the file name, index, and caption. And if you look, as we know that for each image there will be a five captions. So, and this is how the textual input data looks like. So for it contains a file name, the index, and this is the caption, right? Till here we are exploring the images and showing the number of captions for image. Now let's see how the caption wordings looks like. So from the caption wordings, what we did was create a vocabulary. So this is the frequency of the word for example, for the word a, it's 62k count, the frequency count. And here we are displaying the top most frequently occurring and the top less frequent occurring words. So if you look at in terms of the most frequent words, a, in, the, on are the most frequently occurring words, and in terms of less frequent words like classic style, pillared, NFL, devotion, kind of a less frequent words. And as a part of text pre-processing, we have some functionality to remove the punctuations, lower characters, special characters, and the numbers, like remove numeric, remove single characters, remove punctuation. And we are cleaning of all our captions. So as we know here, like for example, uh, yeah, yeah, like a black dog and a tricolored dog. So you could see like tricolored is an hyphen, but as we come here after text cleanup, so a black dog and a tricolored, there is no hyphen. So that kind of a processing has been happened. And then like we are prefixing like a start sequence, and it is like for that as we know that one of the input model, like we need to provide like encoder decoder, we need to provide during a training the output as well. Now we will go into the CNN model. One of the CNN model, the ResNet being trained on the image dataset, ImageNet. So we are making use of the concept of the transfer learning. So to get the feature for our images, and as the ResNet model, so it has these number of layers, and and we will go till the last layer, till the last but one layer, because we don't want to see the predictions of classification, because as that resonant model is used for classification, but we don't want to the last layer. Instead we have to go till this last layer to add those feature embeddings, like vector embeddings for that image. So what we do is making use of the functional API. So we create a model, like taking the inputs of the resonant model input, and the outputs is the last layer is an output. So this is how the recreated model making use of the resonant looks like. And this is the the sample, like taking a single image and creating a prediction, or basically extracting the features of out of that custom resonant model which we have just now created. So this is how the features vectors look like of 2048 in length. And now, considering we have large number of images around 8K, we are considering around 5K for the feature extractions and store them into the image. Like since to work with out of 8K images, we are considering the 5K images. Yeah. So now for each of the images, so we got the feature vector. So now coming to the textual data, right? So So what we do is, for a textual data, we created a data frame of the image, the index, and then the caption, right? So what we will do is, so we will take the caption associated with the index 0. So that way we have like, considering 5K images, so we will be having 5K captions for our modeling purpose. So yeah, this is the code. Like we have like file names and then the D captions. Basically, what we do is we take the caption associated at the location 0, that because we are keeping the index, so considering only the 0. So we take those caption associated at the index 0 for each image, and then the array of D images is nothing but the dimension for those 5K images after applying our custom model using the ResNet. So and then we use the tokenizer for tokenizing our captions, and from a vocabulary size 35363, and this is how the token embeddings looks like for our captions. So and we split the data like into the test and the validation data set. So in terms of like a 20% for the test and the validation, and the sequence length, and for each caption, so out of those 5K captions. The max length associated with one of the caption is 28. So what we do is, for the captions of lesser in length, we basically pad it to of length 28, and the padding will be padded with the zeros. And as we see here, so we do create the training data and the validation data. So and for our model, the input is the text data and the image data, and the output is the the predicted word, the probability word. So if you look at this from the shapes perspective, so we do have like 28 in length. This is like because, as we just saw, that the max length for the token is 28. So that's where like these number of rows with 28 in length, and then this number of images with this 2048 in length, because we need to have in zip it together. That's where like the image gets repeated for these number of captions. And then we do got 3563 because this is the vocabulary in size, right? Now when we start building our model, so the first thing is, so we as we know that for each of the images, so we do have like a feature vectors, right? Feature matrix. So that will be served as an input, and then we have like dropout layer to overcome the overfitting problem, and then we pass it to the dense layer, like of 256 neurons. And then we, for the sequence model, so we use the embedding for our input of that vocabulary size, and we have a dropout, and then we have like a LSTM layer with 256 cells, and that will be our like a feature text. And the output of these two get concatenated, but gets added to our decoder. And the decoder again, it's a layer with 256 neurons with activation of ReLU, and that output gets passed to another dense layer with a softmax function, because we of vocabulary size. That way we get a probability for all our words which are like which are equal, which are in equal in number to the vocabulary in size. So basically, for our model, the inputs is the input image, the feature of the image, and then the input text, basically the word embeddings pass through the LSTM layer, and the outputs is the predicted word. So this is our model. And we have like a cross entropy, and the optimizer is the Adam. These are the metrics. So and then the model summary, if you look at uh, the model summary, so these are like total number of trainable parameters, and the non-trainable parameters are 0. And if you plot the model, as we can see, the from a LSTM perspective, this is one flow, and for the image feature extraction, this is one flow, and this both of them gets concatenated and passed into the feed forward network having dense layer, and then with the softmax function. So when we trained our data, like so we ran for 20 epochs, and we could see that, yeah, there is a considerable like the validation loss tend to go down till fifth epoch, and after the sixth epoch it tend to increase, so because of overfitting of our data. So that's where like when we retrained our model just with 8 epochs, and then started predicting, like creating, what we did was we took some sample data from the image, from the test data set, and then started predicting the caption for those images. So when we started predicting, so uh, for the prediction, we don't need to uh, we pass the output embedding. So what does that mean is, if you look at this, right, prediction of caption, like we just pass in the image. So once we pass in the image, so the model predict of image, and the sequence is like the start sequence, because we get started with the start sequence, right? And we don't need the output because we are predicting the output here. So and for each word predicted, we just want to check whether is that the end sequence. If it is not, again we are sending it as then text, like start sequence space the predicted word. Again it gets sent into the model prediction, which generates a next word. Again that word is sent till we get the end of the sequence. So this is how the predicted caption looks like for the images, like goalie eats the puck in the puck, like man in the red jacket and the red mask arms, boy in the red shirt is stating like few of the sample of the output prediction, and then saving that model in your H5 file. That way, in the next run, you can just load this file and start predicting. And in terms of evaluation for bilingual evaluation, so making use of the blue scores to measure the machine generated caption versus the human labeled captions. So as in all, as I mentioned, the blue scores were quite low. The reason because we are not using attention mechanism architecture like a transformer architecture, and the amount of data set that is being trained on is less, like 5k images. Maybe we could pick a data set which is larger in number, like around 30k images or 50k images, that would yield a better results. So, so overall, this project aims at producing the textual description for an image. You can call it as image captioning or image to sentence generation that can be used for various use cases, like helping the navigation or improving the security on the surveillance cameras, etc. Thank you very much for an opportunity. Thank you very much. Bye bye.